Yeah. Okay. The final talk of the day. We have Fabrizio Barroero from Roma Tre, and he will tell us about the Zilber-Pink conjecture for complex Abelian varieties and distinguished categories. Thank you very much, guys. And let me thank the organizers for giving me the opportunity to come to Israel for the first time, and of course to speak here. So what I will talk about today is I should throw on the thing I forgot. So I will also give people time to come in. Okay, so what I will talk about today is joint work, the result of joint work with Gabriel Bill from Hanover. So let me start with a little bit of setting. No problem. Come in. A little bit of setting, just a tiny bit. So for the whole talk, K is an algebraically closed field of characteristic 0. So varieties will be automatically reduced, irreducible. When I say a variety, I mean over K. Sometimes I will specify what K is. And when I say subvarieties, curves, they're all closed in their ambient space. So what we will look at are, so we will have an ambient variety, an object X. This is not any variety. This is a variety with a structure, with a certain structure. So we, now I'm very, very vague, I know. But so this will be a power of GM, an abelian variety, semi-abelian variety, a pure Shimura variety, things, objects in which we do unlikely intersection. Okay, and so the important thing is that this ambient space X comes equipped with special and weakly special subvarieties. So it comes with and an important thing is that special subvarieties are usually a countable collection of subvarieties. So, example. First example is just a semi-abelian variety. So, if you take semi-abelian variety, so then the special subvarieties, what we usually call special subvarieties, are torsion cosets. So this would be, you take a semi-abelian subvariety, so a connected algebraic subgroup, and you translate it by a torsion point. Equivalently, these special subvarieties are just the components of the algebraic subgroup. Nothing more than that. And then weakly special subvarieties, these are just cosets. So instead of translating a semi-abelian subvariety by a torsion point, you're allowed to translate by any rational point. All right. Example 1.1. This is one of the most concrete example I can give you. Just take a power of an elliptic curve. So this P is an elliptic curve. So this would be your X. And just to give you an example of what special and weakly special subvarieties are in this case. So special subvarieties are components of algebraic subsets. So let me write like this, of things defined by relation. So if on here, so the point is just a tuple of points on the elliptic curve. So special subvarieties will be components of things defined by just linear relations between the points. So this is the elementary, the zero of the group, and and the AIs are just elements in the endomorphism ring of A. So usually Z or some larger ring. Okay, so and then the weakly special ones, let me say something more. So special, so you might have many of these equations, and the more independent equations you have, the lower the dimension of your special subvarieties, and special points are just, in this case, tuples of torsion points. So special points are torsion points when you have when you are in this semi-abelian variety. Okay, just imagine. I mean, if you have G independent relations like this, you basically then have just all the PIs are torsion. And while weakly special, you allow here instead of zero any rational. Okay, so you still have equations that are. So you should think of weakly and weakly special and special subvarieties as subvarieties that are defined by things, by equations that are very much related to, in this case, to the group structure of the ambient space. Okay. So yeah. So if you have a weakly special subvariety, you would allow a point here instead of zero. Okay. So in this setting, I will first state this statement. So this is Manning-Mumford conjecture, but this is not a conjecture anymore. So it's a long time. So this is due to Michel Laurent, Reynaud, Hendry. For different cases, so Laurent did it for powers of GM, Reynaud for abelian varieties, and Hendry for semi-abelian varieties. And this is a simple statement. It just says that if you have a subvariety of your semi-abelian variety G, then this contains at most finitely many to change pen. Finally, remind me if it doesn't, you can't see anymore because I can see actually. But, okay, so finally many maximal special subvarieties. So what does this mean? It means that either your B was special, or basically the special subvarieties are a proper closed subset. Okay, so there is so the special subvarieties that are contained in V are somehow well behaved from the viewpoint of Zariski topology. You can't have any weird thing going on. And equivalently, you can rephrase this but just saying that the special subvarieties are exactly the subvarieties of G that have Zariski dense set of special. Okay, I want to go very quickly in the most concrete case of this. You can just take so what is this in GM squared? This is the easiest, in my opinion, my easiest non-trivial instance of Manning-Mumford. This is a theorem of Ihara and Tate from the 60s, I think, and this just says that an equation like this has over C. This is over C. So a complex plane curve, an irreducible complex plane curve, has finitely many solutions that are roots of unity, so pairs of roots of unities that would give you zero of this polynomial, unless this polynomial is of the divides. So F divides something like this, or So these are exactly the equations that define algebraic subgroups of GM squared. Okay. Okay. The second example. I know I'm going to make lists of these. Let's see if I can. For the moment. Okay. So second example is pure Shimura varieties. Actually connected pure Shimura varieties. And here we have as more concrete examples this AG or even more concretely y1 to the n. So these are just, well, this is just the modular space of principally polarized abelian varieties of dimension G. And these, so y1 is just a1. So this is just the space of J invariants of elliptic curves. Okay, so and you take tuples. These are just parameterized tuples of n tuples of elliptic curves. Nothing more than this. And now I don't want to write down anything. So usually, so what are special subvarieties here? For instance, here are usually not always. So now this parameterizes abelian varieties, and the generic point here, the generic abelian variety has endomorphism ring integers. And usually, not always, special subvarieties parameterize abelian varieties that have a larger endomorphism ring. You might have, you know, so the generic abelian variety is simple, so it's not isogenous to a product of other abelian varieties, but so special subvarieties might correspond to a splitting like this, or it might correspond to just to a larger endomorphism. And here, what are special subvarieties here? Well, again, larger endomorphism ring, which means either you have some components that are CMs, or you have pairs, you have isogenies between the elliptic curves that correspond. Okay. All right. So, and I don't want to write everything down, but the analogous statement, the minimum for conjecture would then be André-Oort. Actually, maybe I can just write on here. André-Oort. And well, the statement is the same. Well, like X here. So, and well, this is now theorem by some people that are here. So I have to figure out this. Okay, the order. So this will be Vila Shankar. And now I can't. Okay. Okay. So in any case, so what do these two statements say for curves? They just say that a curve is either special or it has finitely many special points. Okay. Well, actually, you expect something more to be true. So let's go back for a moment to no, we'll just stay here. So to the case of powers of elliptic curves. So here you have you just take a curve in X here. Take a curve in this X. Then what are the special points in? There are just tuples of special points are components of zero-dimensional algebraic subgroups. Okay, so what you're doing is you have your curve, you're intersecting the curve with a zero-dimensional algebraic subgroup, and so this is this doesn't have an intersection usually. You would expect these two things not to intersect, but then okay, you let your zero-dimensional algebraic, your finite algebraic subgroup vary in the set of all algebraic subgroups, and you still expect the intersection to be small. Okay, well, but if I start with a curve, okay, if I intersect a curve with a hypersurface, then well, they should intersect. If I intersect a curve with something of codimension 2, then they should not intersect. Oh, okay, so this is maybe the guiding philosophy of what I am about to, what's coming next. So what if I intersect a curve with the union of algebraic subgroup of codimension at least 2? So we expect that this is small, fine. So at least not Zariski, well, not Zariski dense, which means small in this case. Okay, so to state some theorems, I need to write down, I will write here because I will try to keep this. So I will give you some more definitions. So now V is a subvariety of X. Now we go back to general X. So this will be either semi-Abelian variety or Shimura variety. And so an important point is that in all these settings, if you intersect two special subvarieties, well, you might be it's possible you get something irreducible, but the components, they are special. Okay, so this is very important because then you can talk about the smallest special subvariety containing a variety, and this is, I will call this, we'll use this notation. This is maybe sometimes I will say the special closure of V. So this is smallest special containing V.
It'll be all of X if you don't have anything next.
What?
It will be all of X if you don't have.
Yeah, of course. Yes. Yeah. So X is special, and actually, usually it's what you want, but yeah. And here I will also, the same is true for weakly special subvarieties. So intersecting weakly special subvarieties, taking components, it gives you something still weakly special. So I will just put a WS here, and this will be the smallest weakly special subvariety containing B. All right, so now I can state prototype theorem. Well, I will just write this. This is a theorem with no content for the moment. I will tell you who proved what in which cases. So this is the curve. Everything is over some K, and again, well, this is the hypothesis you were talking about. I take a curve that is not contained in any proper special subvariety. So the special closure is X. Then, if I look, oh, I'm writing too large here. Well, if I look at the points, I take the points of K such that, well, such that they lie in special subvariety of codimension at least 2. So how do I write it? I write it. Closure of P. This is the smallest special subvariety that contains P. This is X dimension at most dimension of X minus 2. This is finite. Okay. So now let me give you some content. So I usually, when I've given this talk previously, and I write a table with names and cases, but it takes too long because there's too many results. So let me just say real quick. Okay, these kind of problems, in my opinion, I think they were considered first by Bombieri, Masser, and Zanier in the case X GM to the N. And then they have, well, under a bit stronger condition than this, I won't go into details. They prove this statement with K equals Q bar. Then this stronger hypothesis I just mentioned was removed by Morin later, and then Bombieri, Masser, Zanier extended Morin's theorem over C. So let me, this would be a good time to remark that just, you know, if you talk an algebraically closed field of characteristic 0, you can just C covers everything. Once you have C, you have everything. Okay. Then okay, let's go. Then in the years in between, let's say 2000 something until the 2010 or so, there has been a lot of works in special cases for abelian varieties. And here there's really a lot of people that worked on this. I will just quickly mention them. So Viada, Raymond, Rattazzi, Carrizzosa, and Galateau, they proved different cases where X is some certain abelian varieties. Sometimes you have these hypotheses, sometimes you have the analog of that stronger hypothesis I mentioned earlier. And then maybe this is, I will write down because this is, it was quite a big breakthrough. So Habeger and Pila, I think in 2016, they proved the case X is any abelian variety over Q bar, and they heavily use homogeneity for this. And then, so, well, then we proved this. I mean, I think we put it on the archive maybe 2 years ago, so maybe a bit more. We extended their work over C, okay, and then what I did with this is also from this here over Q bar. This is maybe I should write names actually. This is Habeger Pila. This is Barroero Deal, and this is me with Lars Kühne and Harry Schmidt. Okay, while in the case of abelian varieties, we have now this covers quite a lot of cases, you see. But in the case of pure Shimura varieties, even the case y1 to the n is not completely solved. So we have some work of Habeger and Pila in here, but well, they need to impose certain hypotheses on C, which I won't talk about. And in the case AG completely open, we have something for A2 work by Dow and Orr. Okay, so I will now say something about this work. And to do that, I need to put down some more definitions. Because actually, the thing is that we didn't only prove this, we proved much more, but to explain to you what we did, I need to introduce some notation that is actually not so hard, but okay, definition. So again, we have this subvariety of our ambient X. So the defect of V is this. Delta V is the difference of the dimension of the special closure of V with the dimension of V. Well, so look at this. What does this measure? This measures how far your V is from a special subvariety. So special subvarieties have defect 0, and the higher the defect, the further you are from special subvariety. Okay, so the same you can do with the weak case. So this is then we call weak defect. We put the WS and we put the WS. Okay. So again, well, analogously, this measures how far you are from a weakly special subvariety. And then we define optimality. I should stay more space. Okay, so then V, I don't know where I should put it. W. So we have our variety V, and we take a subvariety here, W. So W is optimal if whenever you go from W to V, so you grow in dimension, so you have a subvariety in between U, the defect must increase. So okay, so imagine this. So this is, I think about this in this way. So you start from W and you go up toward V, toward V. Wait, I should. So W is optimal for V. This is of course relative to V. Optimal for V in X. Okay, I should. Right. So you go toward V, and the special and whatever is in between is somehow further away from a special subvariety than what than how W was. Okay, and again you can do the same with weakly special. So this would be weakly optimal.
B is B special or B is
No, V is and nothing. V is a subvariety. Yeah, yeah. So V is always optimal for itself because well, there's just nothing in between, and
it's hard to distinguish the V
sorry. Yes. I will just use. Yes. Thank you. Maybe I just call this Y.
Yeah.
My V's will be Y. I will. This will mess up everything. I'll tell you, but I will make a mess out of it. But okay.
Does that mean W becomes more and more Y?
Sorry.
Does this mean that W becomes more and more Y?
Well, I think about this maybe saying, well, it becomes more, it becomes closer to, it's closer to the structure of your X, to the so yeah, so if X is an abelian variety, then W is closer to an algebraic subgroup than U, for instance. If the defect increases, it means U is further away from it.
So
Yeah.
U is Y, right?
No. Y is your ambient. Maybe I should have. Wait, let me go back to V and I will. Sorry. It's better to change the U. Sorry. So this will be a Y. Everything in between is further away from a special subvariety.
Okay.
So weakly, then we would be WS and WS. Okay, so now I can formulate Zilber-Pink. Yes.
You said for the defect of V measures how much V is far away.
Yes.
Being special stuff, right?
Yes.
So if the defect of V is 0, that doesn't necessarily mean.
Yes. So yeah, 0. Yeah. These are irreducible.
Oh, okay.
Yeah. So yeah. So everything here is irreducible. So if this is 0, then V and its closure are the same.
Okay.
Yeah. So defects 0 are exactly the special and so on. Okay. Maybe before stating, I will just translate the theorem real quick. So the theorem then says, so look at, so if the closure of C is X, special closure of C is X, it means that the defect of C is exactly dimension of X minus 1. Okay? So what are these points? These points, so of course there was a dimension here missing. So this is the defect of P, because P is dimension 0. So the defect of a point is the dimension of its special closure. So this means the defect of P is smaller or equal than dimension of x minus 2, which is smaller than dimension of x minus 1. So the points I'm considering here are exactly the optimal points. So so this is the defect of B, and this is strictly smaller than the defect of C. So these are these optimal of the for B for C. Okay, so this theorem says that C contains at most finitely many optimal points, and this is what the conjecture says. Now I should have left more space here. Okay, so let me. I want to keep this board. If I start erasing this board, please stop me. So the conjecture then is just this is a version of Zilber-Pink. So if you have V in X, then V contains at most finitely many optimal subvarieties. Okay, so I will give so our result is basically an implication of instances of this conjecture. So I need to write down a piece of notation here. So I will say I will do this. So I will just fix two non-negative integers d and m, and then I will say that z p x m d holds. So this will be a statement. This holds if for every v in X of dimension at most m, V contains at most finitely many optimal subvarieties of defect at most D. So bounding the dimensional and the defect will allow me to prove some implications of statements. Okay, but the general Zilber-Pink would be take what I wrote originally. Okay, so this formulation is, I think, due to it's in that paper of Habeger and Pila, but you might be more familiar with the versions of by Zilber. Well, usually Zilber, these versions would talk about maximal atypical subvarieties. If you are familiar with that, maximal atypical subvarieties are always optimal. The other implication doesn't hold, but it's not so hard to prove that this formulation of this conjecture is equivalent to the one of Zilber. You might be, on the other hand, you might be more familiar with Pink's version. And Pink's version is a bit different, and it's not so clear that is equivalent to this statement. Okay, we actually in the paper we prove under some conditions we prove that equivalencies of statements. Okay. Anyways, maybe I will just give a quick remark that this statement. Well, yeah. So this statement, if V is a hypersurface, this is nothing but Manning-Mumford or Andre or this a statement about special points. Why is that? Because if V is a hypersurface, then the defect of V, so either V is special, so if V is special, there is nothing to do, it's the only optimal thing in itself, trivial. If V has defect 1, So V is a hypersurface, so it has the codimension one. These are the only two possibilities. And this is equivalent to say that V is not special. And so optimal things in here are things that have defect. So you see, look here at the defect, the definition of optimal. So this means that the defect of W is strictly smaller than the defect of V. Okay, if we are talking about the proper subvariety. If W is proper subvariety of V, then this means that the defect of W is smaller than the defect of V, and then optimal subvarieties here. Well, V is optimal in itself, but the proper optimal subvarieties for V are special. Okay, maximal special, and then the statement of this is just Manning-Mumford. It's given by Manning-Mumford or Andre or well, yeah, the statement it depends on the ambient. Okay, so now I want to tell you something more about our result. Because we prove something more. So if you have questions, please ask. Maybe it's a good time to remark that this is this conjecture is in this generality is completely open, and it's very general, and I don't have time to show you this, but this, for instance, for Abelian varieties, well, it's clear that this contains Andre Oort, Manning-Mumford, and everything. But this implies Mordel's conjecture, so Falking's theorem. It implies Mordel-Lang, so it implies a lot of statements in Diophantine geometry. So this is a very far-reaching generalization of these statements that were proven in Diophantine geometry. Okay. So to state my theorem with Gabriel, I give you one more definition. So our first work is in the setting of Abelian varieties. So for the moment, A is an Abelian variety. And well, I need to define, this will be a definition in brackets, because this is not the formal correct definition, but it gives the idea more. So I need to tell you what the trace is, the trace of A. So T is the, okay, so this will be over Q. K over Q bar trace. Okay. If it is the largest Abelian variety defined over Q bar that can be embedded in A. Okay, so this the correct definition is well, we have a universal property, but I don't want to go into this now.
That's like the correct definition is like Lang different or something?
Sorry?
It comes from Serge Lang or something, this definition?
I'm not sure who was the first one talking about it. But so you should think about this, you know, like in the example of, you know, you have a product of elliptic curves. Some are defined over Q bar, some are not. And well, the product of the ones that are defined over Q bar are the trace of the whole product. Yeah, I think about it in these ways. Well, this is the easiest example. Okay. So the theorem then, this is so again, these are non-negative integers. A is an Abelian variety over K, and E is its K or Q bar trace. Then, if you prove that statement for T, you have it for A with the same M and D. So now we do have, so then T is over Q bar. So we have some statements over Q bar. So Haberger and Pila proved, of course, ZP. So if A is over Q bar, we proved ZP and so for thirds, no? So there will be one E. But they also proved ZP A and 1. So what is this? So you only look at optimal subvarieties that have defect at most 1. So why did I mention this? Because well, if you have so if you have an abelian variety of dimension 4, well, actually maybe most 4, then a V in A. Well, okay, let's forget about the all A and a point. So non-trivial, you have a curve, and then this is covered by this. You have a threefold, so an hypersurface, and this is covered by, well, in this case, my Mumford. And now what is left is the surface, but the surface has defect at most 2. So optimal subvarieties of a surface in a fourfold, in an abelian variety of dimension at most 4, have defect at most 1. Okay, so I will just in this case, defect of V is at most 2. So proper optimal have defect. So if W is proper optimal for V, the defect of W is at most 1. And then we have this thing. So if A is dimension at most 4, we have Zilber-Pink. And then this means that unconditionally we have Zilber-Pink if the trace has dimension at most 4. Right? If the trace, yeah.
So is it somehow also the case that the ones with the optimal ones that come from the T?
What do you? No, I mean.
So at least for, I guess, it makes sense. You need the V to be over the same.
Yeah. So this is so the V are defined over the field of definition of X.
Right.
So this is a statement about extending the. So if you have a statement for for things over Q bar, you have a statement for things over K.
The trace can be 0, right?
The trace can be 0. Yeah, I'm not sure I understand the question.
So for example, if the trace is 0, it still can be the case of the R, you know.
Yeah, sure. Yes. Yeah, I will give you an example. Well, let me write this down and then I give you an example. So if the dimension of the trace is at most 4, then we have the whole conjecture. So for all M and D. So in particular, example, you have a power of an elliptic curve. So then the field of the smallest field of definition of E is just Q adjoint the J invariant of E. So if the J invariant of E is not algebraic, then you have the conjecture. Okay. So the whole conjecture. So this is, we were quite happy to prove this because there are not many results that that beside curves, hypersurfaces, and surfaces, and so on. So this we were quite happy to discover this. Still, of course, well, this just means that when somebody needs to prove the Q-bar case. Well, it was the case already before, but this is even more, points it out even more. Okay, we also proved other things in this paper. We proved the equivalence of formulation. So we proved that this formulation is equivalent to Pink's formulation, which is not obvious. And also we proved that one can reduce this statement to finiteness of optimal singleton. So at the end of the day, you just need to look at optimal points. Okay, I won't go into this, but I want to mention some ingredients. Okay. I want to mention some ingredients, and I want to mention a bit about how we prove this real quick. We actually, the first thing is that the first reduction is done like this. So your K might be actually larger than the minimal field of definition of A. So this is the first reduction we do. We prove that if you have the statement over the minimal field of definition of A, then you have it for A. And then we do the second reduction. Okay, the second reduction that is actually, well, the one, so this one, K is the minimal field of definition of A. And for that, we use, we need to go to modulate to the universal family, well, sub-varieties of, well, families of abelian varieties and so, and now I'll give you a bit more details. So these I should also put a video. One important ingredient that also appeared in work of Haberger and Pila is what is called the defect condition. So this is the theorem. Sorry, I just write HP because I wrote it many times. Okay, so this just says that if you have W in V in A, then if you take this difference of defects, this is smaller or equal than if you take the one with W. And this implies somehow that actually optimal subvarieties are weakly optimal, which is also nice. So why is it nice? Because then one uses what is sometimes called structure theorem. So imagine like we want to prove this, and then, okay, we have an optimal subvariety. These things implies that we actually have a weakly optimal subvariety, and then the structure theorem comes in. This is in the case of abelian varieties due to Ramon. And just says, I won't write everything down, but if you fix your V in A, then there exists a finite set of abelian subvarieties of A, such that if W in V is weakly optimal, for V, then the weakly special closure of W is so a weakly special closure is a coset, no? A weakly special subvariety of A is a coset. So B finite set S of algebraic subvarieties, your B comes from S, and P is some rational point. Okay, so what does this say in words? Just that if you have a weakly optimal subvariety, then its weakly special closure is a coset of an abelian subvariety that comes from a finite set. Okay, so think about it in this way. Think about this like as C to the n, and then cosets are just affine subvarieties. Okay, what does this say? Is that if you have a weakly optimal thing, the direction of its weakly special closure, it comes from a finite set. You have finitely many directions. Okay, so of course your S depends on V, but once you fix the V, the weakly optimal ones inside, and they come from fixed direction. This is a good way of thinking about this. In any case, so this is due to Raymond, and we use this to do the first reduction, and to do the second reduction, we prove a variant of this defect condition for families, and we use an analog of this for families of abelian varieties, which was proved by Gao in 2020. Actually, this is as a consequence of this Axe-Shanwell, so that was mentioned today. So actually, this kind of results. Well, I don't think Ramon has proved any Axe-Shanwell. He didn't use Axe-Shanwell, but let's say evolutions of these or descendants of this theorem are usually proved via Axe-Shanwell. So again, that's homonomiality comes in for the Axe-Shanwell. So anyways, I'm almost out of time, but I want to say that so we realized doing this work that everything we did was very much formal. It had not much to do with abelian varieties. Well, the ingredients we used, of course, are, but given them, well, everything was very formal. So we introduced, we tried to, prove as much as we could, and we introduced axioms, so that we wanted to put everything together. So semi-abelian varieties, pure and mixed Shimura varieties. So we defined, Gal earlier told me that gave me permission to go over time, but I'm not sure you will be happy about it. So I will try to be cool. I don't wanna bother you. Actually, there's a reception downstairs waiting for us, so there's a prize. That's the final prize for listening to me. It's okay. So we define distinguished categories. Well, we call them like that. Distinguished. So we have a category, and with the objects and the morphisms, and and then we have a functor from the objects from this category to the category K is fixed. And so this is a functor from the category to the category of varieties over K. And well, the thing is this. So for instance, I will just give you examples. So here you could take semi-abelian varieties, and then the morphisms would be homomorphisms of algebraic groups, composed with the translations by torsion points. Translation by torsion. Or, well, of course, you can take subcategories of these. So you can take abelian varieties, you can take GM to the n, you can take powers of elliptic curves. And other examples are mixed, connected mixed. No. Well, the objects here, so actually all of this was because of this Shimura variety That's so. The problem is we need to talk about to use this categorical setting, because with Shimura variety, pure and mixed Shimura varieties, you need to keep track of the Shimura. If you don't know, and if you don't know what I'm about to say, it's not important. But so we need to keep track of the Shimura datum and the arithmetic subgroups. So here you would have, a connected pure or mixed Shimura datum, something like this, and here you would have Shimura morphism, and of course, then this functor would send this thing to the pure or mixed Shimura variety you obtain with this thing. In any case, this is not important. The thing is that we formulated. So these we call them the objects we call distinguished varieties, and these we call distinguished morphisms. And well, we formulated 4 axioms. I won't write them down. Well, for instance, the first one says that you have a direct product. So if you take 2 distinguished varieties, you have a third one that maps via F to the product, to the direct product of the starting 2 varieties. The second one is similar, but it's about fiber products. Well, it's more articulated, but it doesn't matter. A3 just gives a final object in the category, and the A4 is just some factorization of distinguished morphism. I mean, it's not important. It's technical, but at the end of the day, we establish these 4 axioms, and then the special subvarieties are just images of So you see it here. You see it here that special subvarieties for semi-abelian varieties are just images of these morphisms. So if X is an object, so this is special, and special is a phi of Y, where it is distinguished. And weakly special subvarieties are I just want to go in the right order. Phi of psi minus 1 of Z, where so phi goes from Y to X, and psi goes from Y to Z, and little z is a k rational point also. So you take a rational point of this, you pull it back here, and then you push it to X. The components of these are the weakly special. Well, it's not very illuminating, but it doesn't matter. At the end of what one can prove is that with the 4 axioms, you have that the components of intersection of specials are special, same thing with weakly. Then you can talk about, you can just do this, everything goes through, and you formulate the conjecture. And we proved some we proved the defect condition in this case, the defect condition, and of course we didn't prove the structure theorem. So we added the structure theorem as a 5th axiom, and in that case we proved then a similar theorem that the one we had before. We also proved the equivalence of formulations and reduction to optimal singleton. I will conclude just, I'm really out of time, so I will just write down one unconditional statement, and then I will let you go to the reception. So I'm also looking forward, It's not so clear.
No, you have to prove it.
But you know, it's his fault. They told me I can go over time. No, it's gonna be quick. It's gonna be quick. So actually, do I still have the theorem? I don't have the theorem anymore. It doesn't matter. So it's just the same theorem as before, but we have it. Well, I will just write one down. Two. So you can take this one. So E is just some this just the Legendre family of elliptic curves. So this is just the family of elliptic curves over P1 minus the right points. And well, then in here, if you have a curve in here, and its closure is everything. And well, the statement is as before. Well, dimension of X2 is finite. So, and here we need, of course, Q-bar statement. So the Q-bar statement is due to, in the isotrivial case, this is Ramon and Viada, and in the non-isotrivial case, this is work of myself and Laura Capuano. So this will be over any field. Of course, this is defined over Q-bar. So actually, I should. So this is a base change of it. Okay. Or another thing we proved is if you have a curve in A2, so these are Abelian parameterized things parameterizing Abelian surfaces, and so and your C cannot be defined over Q bar, then you have this state. Yeah, no, then I'm really looking forward to it. I'm sorry. Okay, thank you. But other people went on the plan before me, so I'm not.
Okay, any questions not about the reception?
And this other remark, in my master, I think there was a very little known theorem by Marx. I think it was 60.
By who?
Which he remember, he doesn't know it. Because he talks about linear relations between subunits. I mean, also, and actually, Laurent proves Modellang and uses common theory, combines model.
Oh, that's good.
And actually, my next question is actually maybe non this one. So he proves actually my method for all commutative values.
Yes.
And can you also make some statements?
So you can take commutative algebraic groups, but then the structure theorem would not hold in general. So the structure theorem, so you will not have this A5, this last axiom, because this is very much false in GA to the n.
Yeah, but if you have multiple.
Yeah. So commutative algebraic groups satisfy the 4 axioms we have, and well, you might find a category that in which you have this. So if you have vectorial extension in certain, you just need to exclude GA because GA is bad.
And so you prove the theorem over, so like for curves in the Abelian, right? So C, but for semi-Abelian, there's something missing.
No, here this is something I could have mentioned. We have also okay, so these are for base changes of things, but so that we don't have Zilber-Pink for semi-Abelian in the general semi-Abelian case.
No, but you managed to do something for Abelian. Basically, my question was
we might be able to do that in the. So for Abelian varieties, we have the structure theorem for families. Okay, that uses X-channel. So now we also have an X-channel for semi-Abelian. Well, for variation of Hodge structures. So this is Bruno Klinger with Gao, and then one needs to prove the structure theorem, and also one needs to characterize special subvarieties in there, and there's some work involved. So we are waiting for people to do that. I will not do that. That Gao said that he has a PhD student yeah. Okay, thanks Fabrizio again.